Let's briefly talk for example 4.4, the benzene and toluene problem. Can the problem actually be solved? Now, we've already been through the solution, so we know it can be solved, but degree of freedom analysis is going to prove to us that we actually can. So here's how we do a degree of freedom analysis. The first thing that we do is we start with the unknowns. So we go through our system and we look at our system and we say, based on the flow diagram for what we have in our system, M1, M2, and M3 are all flows that are currently unknown. We don't have values for any of these. We also don't know the composition of benzene or toluene in the final product. However, we do know that there is a relationship between the two. So there's technically four unknowns because we're just counting one of these two things because we know the relationship between the two. So we have four unknowns in this system. So that's what you always start with a degree of freedom analysis. The next thing that we do is we look at independent balances. And the best way to think about this is balances on different species. That's key here. So let's look at our system. In our system, we have two species, benzene and toluene, which means that we can write two independent balances. Now, the overall balance cannot be an independent balance because it has both species, benzene and toluene. So when we're looking for specifically independent balances, we're talking about the number of species because one will be only in terms of benzene and one will only be in terms of toluene. Therefore, they're independent of each other. The next thing that we do is we go through and we see, are there any other relationships that we can exploit in order to help us solve? So in this particular problem, we knew the volume coming in and we knew the density. And we knew that the density and the volume had a relationship to the mass flow in one. So therefore, there's one relationship that we can exploit to help us solve this problem. Then we go and we look through and we see if there's any other information related to the problem that can help us solve this problem. And in this particular problem, we knew that 8% of B, benzene, that was in stream one, is what's going to be the mass of benzene in stream two. So we had one additional piece of information. So taking all of those four steps, the degree of freedom analysis goes like this. You start with the number of unknowns, you subtract the number of balances, you subtract the number of relationships, subtract the extra pieces of info, and then the final number tells you your degree of freedom. So we have 0 degrees of freedom, so this problem is solvable, right? Just like we found in the actual problem. Now, if our degrees of freedom had been greater than 0, this is an unsolvable problem because it's what we call underspecified. There's not enough information to solve. We can also have degrees of freedom less than 0, which means we have redundant or extra information, and this is an overspecified problem. So we hope most of the time that we have solvable problems, but real world problems sometimes are underspecified. This is why we always have to go talk to our clients as real world engineers. So this is an example of a degree of freedom analysis. We're going to start to see these in subsequent problems, and we're going to use this as a way to help us figure out whether or not we can solve problems.